everyone, this is Pavi here, and thank you for your interest in this talk. So, I'm a senior data scientist at Great Ormond Street Hospital, and today I'm going to be talking about how we use natural language processing techniques in our projects. So, to give you an introduction about Great Ormond Street Hospital, it is a pediatric hospital, and together with UCL, it's UK's only academic biomedical research center. It is also the first hospital to achieve the HIMSS 7 International Digital Maturity Benchmark. So, within GOSH, I'm part of the Drive unit, and our vision at Drive is to establish GOSH as a intelligent research hospital and also to be the go-to center for pediatric innovation. So we also have a 5-year collaboration partnership with Roche, and this project that I'm going to be talking about has been completed as part of this collaboration. To give you an introduction, so we all know that the data present in different electronic patient record systems, they contain both structured and unstructured information. But often what we found is that most of the structured or relevant information is present in these unstructured data, and extraction of these relevant information is a challenging and complex process. So this is where natural language processing techniques have helped us in discovering the relevant information from unstructured data like reports, patient notes, and so on. And today I'm going to be talking about one example use case, which is how do we extract these structured data from genomic reports. But we are also working on other reports like cardiac MRI reports, where we find that a lot of structured information is actually present in these unstructured data like PDF documents. So what we mean by these genomic reports is genomic testing is widely used within the NHS in the UK, and it has the potential to help us to understand how our genetic makeup has an impact on our health. And these are sequenced in genomic laboratory hubs within the country, and Great Ormond Street Hospital is one of those hubs. And what happens is once it has been sequenced, clinical scientists interpret the results and they write test reports, and often these reports contain a lot of structured data, tables, and free text. And finally, what we see is a PDF document of these reports. So here I'm showing you a few examples. So these are publicly available documents, just to show you the heterogeneity in the layout. And it's not just the templates of these documents. If we look closely, the linguistic structure or the way it has been written is actually dependent on the diagnosis. So in some cases, you might find that gene names or variant names are used, whereas in some cases, like if you see here, they are represented as exons, and in other cases, they could be represented as DNA change ID and protein change ID. So these are all the challenges that we faced when we were looking into this project. And this is a proof of concept where we developed a tool to extract the relevant information from genomic PDF reports and convert them into a structured data. So the how we got this structured data is we had an annotation guideline from experts, and then we also had a biomed student who was asked to annotate PDF documents to extract all these structured data. So this pipeline that we've developed has two sub-pipelines, one where we do document classification and the other where the actual extraction happens. And before I talk about the document classification step, just to give you an overview of the scenario, when we started this proof of concept, we were also building our infrastructure so that we are able to process large volume of documents. So at that time, we had a very limited infrastructure with very limited compute. So we wanted to use techniques that were very simple, that doesn't require much compute power. And the reason why we had to do this document classification is, again, we didn't have a straightforward filtering approach where we can query the electronic patient record systems and ask, like, where are these genomic reports? So we had to get all the documents out. And as part of this POC, again, we just wanted to focus on mission readable documents. So we extracted all the mission readable documents and then classified them as genomic reports or other documents. And the way we did this was we collected roughly around 16,000 documents, and we used an open source pre-trained named entity recognition model. It's called HuntFlare to detect the gene names in these documents. So if a document had like a n number of gene names, we then considered that to be a genomic report. And we roughly had around 400 genomic reports from these documents. And this took us like 2 days because of the limited compute issues. And because it's not a feasible solution, what we did was we had a human in the loop, and we asked them to look through these documents manually and extract potential key phrases that does not overlap with other documents. Like for example, the word genetic could be present in a referral letter, so which is not a genomic report. So we wanted to identify key phrases that don't overlap, and these key phrases were then used to do this classification. And from these 400 genomic reports, we around 384 were detected correctly. So we moving forward, we just use these key phrases to do this classification. And the next step, as I mentioned before, because the linguistic structure or the way it is written is dependent on the diagnosis, so we wanted to extract the diagnosis from these reports and also the organization name. And the reason why we wanted to pick the organization name is if we look through the documents and look through the section titles, they did not actually correlate with the content within the section. So, for example, in one report, we found that a section title called result had a summary, whereas in another report, it would be called as a result summary. So, we had to do this mapping for the templates. And once this is done, we then went on to classify, detect all the tables in these reports and then classify them, like based on whether it contains patient information, whether it contains information about the gene variant results, does it contain any panel information. And then we also detected the different sections and extracted them. And the reason to do this is if we look through a report, it's not very straightforward. So not all the information is provided in an orderly manner. So some of the information might be present in a table, and other information related to the variants could be present in different parts of the section. So this is where we used different NLP techniques and models to extract the structured data. So the first technique that really helped us was sentence tokenizer, because once we were able to tokenize them into sentences, it was quite easier to just use rule-based approaches to extract the structured information. And although out of the box tokenizers may not work quite well, we found it to be useful for this proof of concept. And the other one, I would say, the backbone of this project was this named entity recognition tagger, the HuntFlare model, which was trained on 31 biomedical data set. And this really helped us because once we are able to detect the variant or the gene names, then using simple rules, we were able to extract most of the structured information related to the gene names just using some simple rules. And being an open source model, it was also very helpful for us because we didn't have to then train our models from scratch. And the other models that we used here was in the report sometimes. So what happens, for each gene or variant information, you have a classification, and sometimes it's not present straightforward in a table. It might be present as a short phrase in a table, or we need to read through the result or interpretation sections to understand what the classification result was. So this is where we had to use two pre-trained models. And why we used this here was we did not have any annotated data. So similar to a few shot setting, what we did for each classification, we collected few examples, and then we used these pre-trained models to get the sentence representation so that we could compare them with the sentences present in the sections, and then whichever was closest to one of the examples, we then used that to categorize the result. And the reason we used two models here is one, because one of the models that we use, which is the BioBERT model, fine-tuned on natural language inference. So this gave us good result when the sentences were complete and grammatically correct. And the other model was the multi-QA-LM model, which was trained on question answering pairs. And this was giving us good results when we had shorter phrases. So this is the overall architecture of the pipeline. So at every stage, what we do is we collect all the data so that for future work, we don't have to go into the PDFs again. So all the tables, all the sections, all the genes detected, whatever structure data we've extracted, we put them in an intermediate output. And the final output is customized to what was required as the final structure data from these reports. And these are the main models that we've used. So we did not use any large huge models, so and it was quite good like using these three models. And so this here is an example report. It is a dummy report of what gets generated at Great Ormond Street. And so here you can see some of the details might be present in a table, some might be in a text. So the same information sometimes may not be in a table, so you need to extract them from the different sections. So different information is present, like it's scattered everywhere in a report. And I'm just gonna run this demo just to show the results. So from this report, we want to extract the patient details, the referral reason, the different sections that talk about the results, and any variant information like the gene list is present, the technical details, if there is any information and evidence, if there's any panel app URLs. And so, going on to the data overview and evaluation, like as I said before, we had a biomed student for 3 months who was asked to manually annotate around 250 documents, which were obtained from different healthcare organizations and also based on different diagnoses like onset epilepsy, cystic fibrosis. And from these 250 documents, there were 120 machine readable ones which we used for evaluation purpose. And in terms of the document classification, the recall, so here we've plotted the recall rate. Most of the reports were classified correctly, but where we missed was in the epilepsy reports, because there are like 20 different epilepsies. So it was quite it wasn't I would say like just using key phrases wasn't sufficient here. So this is something that we are looking as a part of the next phase. And in terms of the result, again, this is based on the recall rate. What we've done here is we're just checking like, has the tool captured all the patient details? Has it captured all the results and interpretation? Has it identified all the variants in a report? And if it has it identified all the information related to all these variants, or some of the information is missing? And we've been a bit strict here. So even if one information was missing, we then consider that to be incomplete. And in most of the cases, it was doing quite well. Where it missed was in terms of epilepsy, we found that older reports did not have a structure, like it did not have sections or tables. So it requires a bit more understanding of the text, and using simple rules was insufficient here. And in terms of neuroblastomas and the muscular dystrophy, the reason here it wasn't able to capture all the information was, again, here it was talking about deletion of exons. It was not like straightforward like variant names. So it requires a bit more understanding of the text, which is what we are looking into in the next phase of work. And so what's next is we are also assessing the reusability of the components. So we want to create more modular components that could be reusable. Like, could we use some of the components that we built here for like cardiac MRI reports or any other reports? And the other thing that we are looking into is to deploy the tool in a prod environment. So right now we've moved the we moved the code base into our on-prem environment, and we've tested it on like working on a large volume of documents. And the next thing is we would want to continually monitor the components to see if we can improve their performance, because 120 documents is quite small. So we wanted to test on more documents and see where it requires more improvements. And as you can see here, this is probably this. It's an older version. There are a lot more large language models that are coming out every day. So we would also want to explore, like, is it where these large language models could be useful because of their potential. In a zero shot or a few shot setting, can we use them rather than training something from scratch, or is would it be used as an annotation tool? So these are some of the things that we are looking into. And the next step, one of the main steps that we want to do, is to look into how do we evaluate the inference data using factual verification. So once we have all these structured data, how do we verify them? How do we know that it's been extracted correctly? So this is something that we want to explore, like maybe use a question answering approach, looking back into the document. So these are the next steps. And so this is our team, and thank you for listening.